201, lecture 37. So last time around, we had come up with this structure as our first candidate for an operational amplifier. This was the output terminal. This was the plus terminal, and this was the minus terminal. I said, let's try and figure out if this does whatever we want. If it has all the properties of the operational amplifier, then we are done and we can move on. If it doesn't, then you figure out what the problems are and you go and fix those problems. Hopefully, you will end up with something which actually approximates the ideal operational amplifier to a better degree. And to that end, what did we say? If somebody claimed that he had a circuit which was an operational amplifier, then what you would do to figure out if what the person is claiming is true or false is to put this in all possible op-amp circuits that you can ever conceive of and make sure that those circuits work as expected. So, if the work is expected, then what is there inside the black box is indeed an operational amplifier, otherwise it isn't. So, to that end, the first thing we said was, let's try and the simplest of circuits that we can build with an op-amp, doesn't require any external components at all, and that is the unity gain follower. Plot this as the op-amp and see what happens inside. So please notice that Vout is connected back to the negative input terminal, and if you want to do that, if you did that with the real circuit, what you will have is a connection of this form. In other words, you would expect that the incremental gain from Vi to Vout would be 1, because that's what you're trying to realize. So you know that if this was an ideal op-amp, the gain from input to output, so Vin, Vout will be 1. So if this was really a good op-amp, then when you connect it from input to output, the gain must be 1. What other properties do you expect to see here? We are expecting to see a gain of 1, input impedance of output impedance is 0. So let's see if that is indeed true. What can we say about the gain now? What is the incremental gain here? The betas of the transistors are all infinity. The output impedance of the PNP transistor is 0. We get for the incremental gain of the amplifier in the open loop without this connection. What was Vi by Vo? No, from here to here. How did we define gain last time? What did we do last time? If this was VCM plus VD and this was VCM minus VD, incrementally this potential is ground. So this current, incremental current is GM times VD. The same incremental current comes here. This current is GM times VD. Alright. And this current is this direction is GM times VT. So, the incremental output is 2GM VT times R. Okay. What is the voltage you have put between these two terminals, between the plus and minus? Please note that this is the plus terminal of the op-amp, this is the minus terminal of the op-amp. So what you have put is 2 VD. So if you want to treat this as an op-amp, the open loop gain is, it is GM-R0. Open loop gain is GM times R0, and that is coming because it is 2 GM VT times R0 divided by 2. You understand? Instead of having infinite gain, we have a finite gain of value GM R0. What do you think is the incremental gain from input to output now? If you actually make this connection, this point to this point, once I close the loop, simply has to be, how do you get GM R0 by 1 plus GM R0? I mean, if all the transistors here are in operating in their active regions, you can model the differentials there. Let's do this before we get to the closed loop. This is the positive terminal of the op-amp. This is the negative terminal of the op-amp. So if all transistors were operating in the active region, then you can model what would be the input impedance? What is the incremental input impedance looking in between this terminal and this terminal? Why is it infinity? The beta is infinity, so there is no R pi at all. Okay, R pi is infinite, so as far as the amplifier is concerned, the input impedance is infinity. The gain is, as we just saw, so the difference between the positive and negative terminal is Vx. Then we already have seen that the gain is A times Vx, where A is Gm times Ro. See, what do you think is the output impedance looking in here? It is simply R0. Alright. So this is the small signal equivalent of the Is that correct? Alright. So now, can you tell me what happens to the incremental gain when you close the loop? Incremental ground. Why is this incremental ground? Why is this ground? Please remember how the incremental circuit came about. We have at this node, if you look at this node, what is the equivalent circuit of the PNP transistor at that node? The R0 between which two terminals? Between incremental R0 is between the emitter of the PNP transistor and the collector of the PNP transistor. The collector of the emitter of the PNP transistor is incrementally grounded because it goes to VCC. So this incremental ground is coming because the VCC is an incremental ground. Does that make sense? This is GM, this is Vx, this is GM Ro times Vx, this is Ro, and what you are doing by closing the loop is connecting the output, okay, like this. And sure enough, as you guys point out, the incremental gain, if I put V in here and have V out here, so the form, this is GM RO by GM RO plus 1. So we already have unearthed the problem. What is the problem? Finite gain. Okay. And as I said, GM is of the order of I by V. RO is of the order of VA by I. The value of the gain, GM R0 is of the order of VA by VT. So several tens of volts by several tens of millivolts. So it's of the order of 100, anywhere between 100 and 1000. Okay. And you know that you want more and more gain for an op-amp. Why do you want as large a gain as possible? In the closed loop properties of the system will be independent of the forward amplifier if the forward amplifier gain is infinite. We want to have as large a gain as possible. Still remember all the negative feedback stuff we did. The closed loop gain is of the form 1 over f times AF by 1 plus AF. So it just means that if you have larger and larger A, you can put a smaller and smaller f, and still AF will be a sufficiently large number, which means that if you have larger and larger A's, okay, or the gain of the op-amp becomes larger and larger, you can realize a larger closed loop gain, okay, because you can make f smaller. The feedback factor, 1 over the feedback factor is the closed loop gain, but if you make f small, the loop gain, which is A times f, becomes small, okay, which causes this AF by AF plus 1 to deviate from unity. One clear thing to do is we must increase the gain from what we have, several hundreds, to maybe, let's say, you want to get maybe 10,000 or 100,000. So any suggestion on what I might be able to do? If I have a gain of 100 and I need a gain of 10,000, what should I do? Okay, one suggestion here is that change the current, increase the current. Does increasing current help here? Because GM increases certainly, but RO decreases, so GM RO is the same. So if you have, two amplifiers of gain 100, you can put two of them together and you'll get a gain of, if you cascade them, you'll get a gain of 10,000. You understand? So, we'll list out all the problems and then we'll put together to all these problems in one shot. So, there's one problem which is finite gain, and we already seem to have an idea of what we need to do to fix it, which is cascade multiple stages and you'll be able to get more gain. What other problem do you see in this circuit here? What is the definition of an ideal op-amp? Large gain. The output impedance must be low. So this is the second problem. The output impedance is the second problem. Alright? So we have already found two problems with the small signal stuff itself. So I only started to think what you will find once you start applying large signal strengths. So the next question is, how high an amplitude can I put here? These are all small signal problems. The next thing is to see what happens when I put in a large signal here. So the usual problem of how large an amplitude I can put before the op-amp goes, the output starts to clip. And when will the output start to clip? When any one of these transistors gets out of the active region and gets either cut off or pushed into saturation. So how high can this voltage go? What is the upper limit of? Yeah. So what do? You find the quiescent voltage everywhere. So the quiescent voltage of the input sine wave is 0. When the quiescent voltage of the input sine wave is 0, what is the output? When this is 0, what is the output? This output should also be 0. 0 volts if I put a sine wave of amplitude A, what will be the output? The incremental gain is virtually 1. So this will also be a signal of amplitude A. Alright? If this is A, how high can this voltage go? Let me label the transistors. Q1, Q2, Q3, Q4. So if the out becomes higher and higher and higher, which devices do you think are most likely to get into the danger zone first? Q4. Why? Please note that it cannot be Q3. Why? The collector and the base are always shorted, so it's always sitting at the edge and nothing changes. Similarly, the same thing for Q2 and Q3 are happy campers. Which do you think are problematic? Which transistors are most likely to screw you up? What is happening to Q1? What is the quiescent potential at this node? VCC minus 0.65 volts. As the input increases, what do you think happens into Q1? As the input increases, Q1 gets pushed towards saturation. Alright? What about Q4? Q4 also moves towards saturation. Why? Because Q4 is please recall, Q4 is a PNP device. So as this potential increases, this potential also increases, which causes Q4, collector of Q4 starts coming closer and closer to the base of Q4. So Q4 is also moving towards saturation. So both these guys are the danger candidates. Alright. So what is the maximum value of A I can put before either of these transistors get saturated? So the upper limit for A is what? It's VCC minus 0.65. So what do you think happens when A goes low? How low can the sine wave go before weird things start happening? In a negative half sine wave cycle, what do you think is the problem? What is the incremental current through Q4? Please look back here. What is the incremental current coming out of the op amp? What is the current flowing in this branch? 0, because there is no base current in this transistor, so the current flowing in that branch is 0. So the incremental current flowing in this transistor must be very, very small, and if RO tends to infinity, it must actually be 0. The only change in this transistor is because of the output impedance of this transistor. The changes in the currents are very small, so no transistor can go to cutoff. Which transistor do you think is a problem? These two voltages are approximately the same because the gain is very large. Correct? What happens to this potential? So, if you think of this as a differential pair, you are applying what, in other words, what kind of signals to the differential pair? These two signals which you are applying to the differential pair has got a big common mode component. And what did we say if these two potentials are identical? What is this potential? Okay, I went through this whole discussion on common mode range of the differential pair. If the common mode input to both these terminals is too low, what will happen? The current source will go into saturation. Why? What is the potential at that node? If this was V1, this was also V1. What is this potential? V1 minus 0.65. Okay. What is the negative limit on A? In the negative half of the sine wave cycle, the input goes for 0.65 volts below this potential. Right? Both these guys are the same. Okay, this potential is the same as this potential, and this potential must be 0.65 volts below these two. So, and that must be at least 0.65 volts above VEE. So, the lower limit for A is VEE plus how much? 1 point. The maximum amplitude of the sine wave you can put in before something bad happens is this chap and the absolute value of this chap. You can never expect signal swings in an amplifier to go all the way up to VCC or all the way down to VEE. There will always be something you lose out at the top and something that you lose out at the bottom. Okay? And 0.65 volts and 1.3 volts seem reasonable numbers, especially knowing that you're not, please note that you're not really wasting anything, in the sense that you're going all the way up to where these devices get into saturation, or this device gets, the devices that go into making this current source get into saturation. Alright? And there's nothing much we can do about it. We have unearthed two problems as far as the small signal operation of the amplifier is concerned. So these are two things which are not satisfactory and we have to fix. Let's see, one more amplifier and see if there are any other problems with the. We have seen a non-inverting amplifier. So one thing to see is, okay, let's try and put our op-amp in an inverting amplifier and see if everything is okay. R, VI, VO. So if the op-amp is ideal, Vout must be equal to minus VI. Now let's see if the same thing holds when we build our, we replace the op-amp with our transistor circuit and build the amplifier with that. So what should I do here? Where should the resistors come? Okay. So which is the negative terminal? Left or right? This is the negative terminal. This is the positive terminal. What should happen to the positive terminal? Must be grounded. The negative terminal must go between the output and transistors are active, we go through the usual arguments. So, if this was a sine wave of amplitude A, what do you think is the amplitude here at this node? It must be minus sine. This must be A. So, is there a problem or are we okay? If V in was 0, what is V out? 0. Okay? V in goes up, and in this fashion, V out will attempt to go down. The moment V in goes up, V out goes down. And what happens? Q2 will go into saturation, thereby causing the sine wave to stop. Is that clear? You understand? So, even if you put an infinitesimally small sine wave, the moment the input goes up, Q2 enters saturation, causing a drop. Okay, so what happens when the input goes in the negative half cycle? When V in goes negative, then this potential will go up, thereby eventually pushing Q4 into saturation. So, it seems as if you can put a fairly large negative swing at the input, but the moment the sine wave goes positive, immediately Q2 gets into the saturation region, thereby causing the output sine wave to distort. On the other hand, the negative part of the sine wave is okay. And the reason why that is happening, if you think about it a little carefully, is the following, which is the lowest that this potential can go to is the base of Q2. In other words, the output swing limit are dictated by the input component. And why does this make sense? The positive half of the input cycle is clipped and the negative half of the cycle is alright. The reason why the positive half of the input cycle is clipped is because these two potentials are if the op-amp is working properly, these two potentials are virtually the same. In other words, the basis of these two differential pairs, are at some common mode voltage, which in this case happens to be ground. And the moment the collector of Q4 and Q2, which is the output of the op-amp, attempts to swing below the base potential of Q2, which happens to be the common mode of the two input signals to the op-amp, Q2 gets into saturation, thereby destroying the high gain property of the op-amp, causing the output of the sine wave to distort. So, clearly, while the op-amp circuit that we had worked quite well for a unity gain amplifier, it doesn't work for an inverting amplifier, so there is hardly any point in continuing on and putting this in various other circuits, because the two circuits that we have considered have already unearthed, a Pandora's box of problems. So the first job is to try and fix these problems rather than attempt to figure out, what other problems are there. Once you fix these problems, then you can do this in other circuits and see if there are any remaining problems. If we're all, I think I will stop here.